Hopefully everybody's doing good tonight. I see you got a couple of people online, a couple of people in person. Let's see. Cool. So for tonight, got a lovely lecture planned. We're going to be looking at exponents and roots. I doubt we're going to get that far, but if we manage to finish everything for exponents and roots, I also have stuff on units of measurement planned, already set up, but that's more likely to be next class. But yeah, we're gonna have fun tonight. Magically February 1st. Tomorrow is 2/2/22. It's Tuesday on a Wednesday. Get that? I'm gonna wait till 2/22 in the afternoon and be like, Tuesday. Everybody at work will be like, God, you're unprofessional. You got to be able to have fun at work, but I work for the state, so they don't care. They don't want to have fun. They want to go get their work done and go home. I don't really blame them. But yes, we'll do exponents. We'll cover what radicals are and all the basic roots. And we'll even cover some of the more complicated roots that I'm not sure that you're actually gonna run into, but I want to teach roots in such a way that if you see them, anything giant and horribly complicated, you'll understand that it's just as easy as one of the basic ones. So they're actually not bad. So, of course, I like to start with some review to keep your brain kind of fresh on stuff we did last time. So last time, if you remember, we did mostly operations with decimals. So adding and subtracting decimals follows the same rules as adding and subtracting integers. We already learned all that stuff. Just you have to make sure that you keep track of the decimal. So you line up your numbers you're working with at the decimal point. And then you place a decimal point right below the line where your sum or difference will be. So you take that decimal point and it lines up right there with your answer the same way as it does with the problem. Multiplying decimals is a little different. You still do the multiplication like you normally do, but you kind of ignore the decimal place at first. You don't have to line it up or anything. In fact, I recommend you don't. And then all you have to do afterwards is say, well, how many decimal places did I have after the decimal point on each of my my starting numbers? And you take that many places from both, add them together, and that's how many places you'll have in your answer. So it'll be fun and exciting. And we're going to do some of those because I don't expect you to remember everything from last time. Heck, I wouldn't. All right, so we got some examples here. I'm going to write out the first one on my notebook here first. A couple of these I found in other worksheets. A couple of these I made up on the fly, so we'll see how ugly it gets. The first one is one that I made up, because of course I did. Okay. So we have 364.245 plus 746.755. Okay. Random piece of fuzz. Okay, I thought that was a dot. Whatever. So you line them up, the top and bottom. Standard convention with addition and subtraction is that you have the biggest one on top. It doesn't matter as much when it comes to addition. It definitely matters when it comes to subtraction. So I'm just going to do it that way every time. That way, less room for error. I'm not going to be, working this a few years from now and be like, God, I don't remember if it was addition or subtraction. I put the bigger one on top. So if you just do it every time, then you're pretty safe. In fact, the only time it truly, truly matters, other than remembering some tricks with subtraction, the only time it truly, truly matters is division. You don't want to screw around with your division. Okay. So let's start adding. You always start from the end. Oh, and don't forget that your period, your decimal point has to come straight down. So here, here, and here, they're all lined up. So 5 and 5 gives us 10. So we have a 0 down here, and we'll carry the 1. 1, 5, and 4 gives us 10. So we have a 0 down here, we carry a 1 again. 7, 2, and 1. 10. Carry a 1. We got 11, all right. 11, yep, all right. 11. Yeah, you could definitely tell I made that problem. Yeah. Math nerds. All right. So when you end up with an answer like this, the main reason I wanted to set one up kind of like this, other than the fact that it was just for funsies, that it's a bunch of ones. But if you end up with one that just has a bunch of zeros at the end, you can drop them. They don't need to be there. You can just say the answer is 1,111. That's perfectly fine. You don't need that unless, again, you're doing a problem and it 100% wants your precision to be down here, then they'll like it to be that far. But realistically, the only time you're ever going to be asked for something to have extra zeros where you don't really need them is if you're doing like some funky science stuff. And at that point, you're going to forget every word I said already, and you're just going to learn it like it was new. So it doesn't matter. Out of my way, pens. Let's look at another. I don't remember what the other one is. Let's look at that. So this one is 267.5 minus 783.24. Okay. So if you remember from before, anytime you are subtracting a larger number from a smaller number and you're doing it on paper, you absolutely must have that larger number on top when it comes to subtraction. There is no way around it. So we kind of have to do these problems backwards when that happens. So we end up subtracting it, this one minus that one, because otherwise the numbers just don't work out. I've tried it the other way around. I tried to find a nice way of making it work. There's not a great way of making it work. The easiest way to deal with these is if you just say, oh, I'm subtracting this one from this one. And remember, hey, I got a small number minus a large number. That means that it's going to be a negative number. So if you have to flip them that way, your answer is going to be negative. And again, in a situation like this, again, we have to make sure that our decimals line up. But if you run into one where there's kind of a gap from our decimals lining up, it's perfectly safe to put an extra 0 there. You don't have to, But if it makes it easier on you, you can go ahead and do it. So just do your standard subtraction. 4 minus 0, 4. 2 minus 5, I can't do that. So I got to borrow. This 3 will become a 2. And this 2 will become a 12. So 12 minus 5, we have a 7. 2 minus 7, again, got to borrow. That becomes a 7 right there. That becomes a 12. 12 minus 7, we have a 5. 7 minus 6, we have a 1. And 7 minus 2, we have a 5. So we have negative 515.74. You always have to remember that negative there if you're flipping these guys around to do your subtraction. You don't have to think of it as some weird special rule. You can always just say, hey, the top one's got to subtract the bottom one. So small minus big, I'm going to end up with a negative. And that negative looks like it's going into my circle because I'm a terrible circler. Terrible penmanship. I think that's where I want to go with it. Let's do more because you guys love these. Never seen such an excitable, happy-go-lucky group. Cool. So this time we have 104.24 minus 78.003. Okay. So we're doing the bigger one minus the smaller one. We don't have to flip anything around, but we do have to make sure that our decimal point lines up. Now notice we have a gap on this one again, but yeah, it's on top as opposed to on bottom. On the bottom over here, it wouldn't have mattered. 4 minus nothing would have still been 4. That one's really easy to not care about. But right here, we don't have anything here and we're subtracting a 3 from it. So we have to make sure that we take care of that somehow. So in these cases, you do want to make sure you put a 0 here, because then it becomes more clear that you can borrow from this 4 here. That becomes a 3. And now this becomes a 10 here. So we just went from having nothing there to having 10 there. All right, so we have 10 minus 3, 7, 3 minus nothing, 3, 2 minus nothing, 2, 4 minus 8. That breaks. That breaks completely, so we're going to have to borrow. But my next digit is a 0. So I can either look at it, there's 2 ways to look at it. I can recognize that since these are on the end, this whole thing is a 10 right here. So I could chop that off and make this whole thing a 9 and put a 1 right here. Or if I'm still really shaky on these and I don't quite understand how it is I'm going to do that, I'm really worried about using more than one spot at a time, more than one digit at a time, which I'm gonna teach assuming that you don't remember how to do anything. It's the safest way to do it, you know? I mean, heck, as you learn more things, you're gonna forget how to add when you're doing harder things. So I mean, it's fun. So let's say that I don't remember I can do that. Let's say that I go to borrow here and I say, uh-oh, I have a 0. What do I do? Well, you would then borrow from the next digit over. And this actually is a good way to do it in general, because if there were more digits over here, I would 100% have to do it this way anyway. So I would borrow from this column. This would become a 0. This one would become a 10. Then I could borrow into this column. This 10 now becomes a 9. This 4 can become a 14. So we see that we have to borrow here. If there's a 0, that column has to borrow first, and then we can borrow from this column into that one. And then we're safe. 14 minus 8, that's a 6. And 9 minus 7, that's a 2. Not too shabby, other than my handwriting. My handwriting is horrible. It's almost like it gets worse. Let's do more. I got 2 more because multiplication. 7.3 times 11.1. So with multiplication, it doesn't necessarily matter which one goes on top and which one goes on bottom, because 2 times 3 is the same as 3 times 2. So you're pretty safe either way. The question is, which way is it going to make your life easier, right? We want to do the least amount of work. I mean, I know it seems like I want everybody to do extra work, but I mean, most of the reason we have multiple methods of doing things is so we can take shortcuts. I like shortcuts, you like shortcuts. Well, remember, whatever number is on the bottom, we end up multiplying through to the top, and then we move down a row, put a 0, and then start multiplying again. And then we move down a row and go to the next digit. So the fact is, I have 3 digits here and I have 2 digits here. It would be easier for me, I'd have less work to do if the 7.3 was on the bottom. So that's the way I'm going to do it. I'm going to do 11.1 times 7.3. That way, I only have to have 2 rows instead of 3. If this one was on the bottom, I would have to do 3. Okay. So remember, we don't have to worry about lining up the decimal places that just coincidentally happen because they both have 1 place afterwards. But when it comes to multiplication, you can just put everything on the right. It's fine. The decimals come later. So you just worry about it as normal. 3 times, well, it's going to be 3 times 1 all the way down. 3 times 1. Next one, 3 times 1. Next one, 3 times 1. We get 333. And note that I'm not going to put a decimal down here. Again, it doesn't matter until we're at the very end. Now we're moving over a digit. And if we're moving over a digit, we start a new line and put a 0 right here. Because remember, we're actually multiplying by 10 times this digit here. So we're actually multiplying kind of by 70 instead of 7. So that's why there's a 0 there. So 7 times 1, 7. 7 times 1, and 7 times 1. So we had 7s all the way down. And now we add these products together. So we had 3 and 0, 3. 3 and 7, that's a 10. Carry that guy. 3 and 7 is a 10, plus that 1 is an 11. Carry that guy. And that turns into an 8. Now, we've already done multiplication. The important part is knowing how to deal with these decimals, right? That's the main thing you're trying to learn here. Don't stress the the multiplication. You've done multiplication, we can do multiplication. If you don't know how to do multiplication, you can watch a YouTube video. The main thing to get down here is how many digits we're going to move over for the decimal place down here. You say how many digits are over here? 1. How many digits are on this one? 1. And you add those together. 1 and 1 gives you 2. So that means there's going to be 2 places after the decimal on this number. So 81.03. Works that way every single time, no exceptions. It's great. It's convenient. Not too bad. Then we have one more example of the multiplication. 0.5 times 0.25. Yeah, this one came out of my head. So as for which one we're going to have on the bottom row, this one has less digits, so I'm going to put this one on the bottom row. So this one will be on the top. 0.25 times 0.5. Set that up. Then we're going to do our multiplication. And the nice thing about these guys is the last digit on the left is a 0. So we really only have to do one row because the next row would just be 0 times everything. It would just poof. So we can do 5 times 5, 25, carry the 2. 5 times 2 is 10 plus 2. So we'd have 12. We don't really need to carry because that's a 0. So we're good there. And then again, we wouldn't have to move over a row and put a 0 and do the multiplication because we have a 0 right here. So we're done, except we're looking at 1/2 times a quarter. So we're not going to have 125. We need to know where that decimal is going to be. So again, you look at your original numbers, say, oh, there's 2 after the decimal place here. There's 1 after the decimal place here. 2 and 1 gives you 3. Well, that means all 3 of these digits are going to be after the decimal place. So it would be 0.125. And generally, you don't want that point to lead. You kind of just want a 0 there as a placeholder. So say, oh, it's nothing 0.125. That makes sense. 1/2 of a quarter is 12.5 cents, I guess you'd say. Makes sense. It works. It works. Any questions on this stuff? Questions, comments, concerns? I think we're good. I think we're good. We have a little bit more review. Because you know I'm not going to leave you without doing more dividing decimals because that's the weirdest part, right? That's the weirdest part. Their least favorite thing. So we gotta jump in. We gotta do it. Gotta make sure that we're not blowing up the universe. So a quick method of dividing decimals. So if you have numbers that are really nice, it works out really neatly, you can do it quickly, it's not going to become a problem. My example is a terrible example because that is kind of a weird problem. But you can multiply both numbers by 10 until you have nothing but integers, and you can divide by reducing or whatever method you really wanted to do. So if I had 45.2 divided by 53.6, I can multiply both of those numbers by 10, and it kind of moves over the decimal place. So it would become 452 over 536. Because at that point, you're just multiplying it by a 10 over a 10, which is a funky looking one. The main thing, way we do it, which we end up using that concept anyway, is long division. So long division, you set up like you normally do. You put the divisor to the left, so the bottom part. You put it to the left of the dividend under the long division sign. If your divisor has a decimal, so what you're dividing by, if that has a decimal, you move that decimal point to the right until it's an integer. You move the dividend decimal the exact same amount of places. You don't care if the dividend has a decimal place, not even a little bit. And then that decimal point, wherever it is in the dividend, it moves straight up on top of the long division symbol. So just directly above where it ends up moving to. And don't worry, we have a couple of problems for that. Granted, I only did 3 problems for that because, well, it's long division, so it's long, but it works. Let me write some stuff down here. So we have 458.8 divided by 31. Okay. Jump over to the share. This is me wondering why in the share screen there's so many blanks with doodles. Really have that many whiteboards? Well, that's the whiteboard. I don't even know. I don't know what I'm looking at. I haven't screwed around with Zoom enough. I mean, hell, I'm using a notebook over Zoom. I could do a whiteboard. I refuse. Okay. So when it comes to division, I just want to cover this one more time. This whole thing could be written like that. I mean, this is the same as that, which is the same as having a division symbol in between. They are all exactly the same. All of them. Doesn't matter how it's written. Every one of these is the same thing. It could be a fraction. It could be straight division. It's the same thing. So remember the top part, or the first part, this is the dividend, and the bottom part is the divisor. You might say, do I really need to remember that? I didn't. I have a degree in this. So probably not. But it sure helps knowing what those are when you're going over this stuff in online learning or textbooks or whatever, because if you don't remember the word, that sucks, but whatever you're reviewing over is going to be using those words. So I'm going to use them. So like any long division problem, we're going to put the dividend under this guy and the divisor on the outside. And the funny part is I actually Googled it because I was curious as to whether or not there was a fancy word for us. You know what this symbol is called right here? This weird little thing right here. That's actually called the long division symbol. It doesn't have a fancy name. They literally just call it a long division symbol. I was a little disappointed, but I got over it really fast because that's a stupid thing to be sad about. So Now we do long division as usual, except remember this decimal point, wherever it is right now, is going to go straight up. We didn't have to shift any decimals over because this guy, our divisor, is already an integer. So we were good to just move that decimal place up. So we take our 31, look at the first two digits over here and say, how many times does 31 go into 45? Once. You take that one, multiply it by your divisor, and put it directly underneath, and subtract. So 45 minus 31, it's going to give you a 14. And every time you bring down your next digit, so 148. Then you would say, okay, well, how many times does 31 go into 148? Well, that's a tricky one. But I know 3 times 5 is 15. So if I multiply this thing by 5, it would be a little over 150, of which this is not. So I'm going to assume 4. We're going to roll with 4. Let's see what happens when I multiply it by 4. Remember, if you're not confident, don't draw on a pen like I am. Let's take that 4, multiply it by 31. 4 times 1 is 4. 4 times 3 is 12. Yeah, so we're good. Do your subtraction. We get 24. Again, we bring down the next digit. You don't need to do the arrows. I'm just doing those for your notes. And then you say, how many times does 31 go into 248? I don't know. I'm not going to pretend to know. I'm not going to pretend to have a fancy way of doing that. I'm going to grab my calculator because why not? The alternate method is to try something and see if it works. Oh, it goes in 8 times. Okay. Well, that makes sense. 3 times 8 is 24 and 3 times 1 is 8. So it actually lines up really nicely. So if I put an 8 there, I would take that 8, multiply it by 31, and I get 248, which gives us no remainder. And since we have no remainder and we're doing long division, we are done. We are done. So 458.8 divided by 31 is 14.8. Any questions on this problem? We got a few more long divisions, so if it's just the method, don't worry, you're going to see some more. Okay. Let's look at the next example I got for you, which is 16.06 divided by 2.2. So, one thing I do want to show you, because we are going to have to shift over the decimal places on this one, but I want to show you guys why it works. And it's basically what I had written as quote unquote quick method on the last slide. Since our aim is to not have a decimal in the divisor, you would look at that and say, well, what would I have to multiply that by to get the decimal to move over? Well, 10, right? 0.2, that's in the 10th place. So if I multiply it by 10, it'll become the ones place. So we take that and multiply it by 10, but remember, we can't just multiply by a random 10. We have to do it as 10 over 10 because that breaks down to a fancy looking 1. So we do that. And basically what happens is the decimal point just moves to the right for however many 10s I have. So the 16.06 becomes 160.6, and down here, this becomes 22. Now that's the concept that we're working with when we do the long division shifting decimals over. And let me show you how that works out. So we have, ignoring I just did anything at all, we have 2.2 going into 16.06. And we know that in long division, our divisor, this guy out here, has to be an integer. Has to be an integer. So you take that decimal point and you shift it over until it is. And you say, how many times did I just shift that over? Once. So you do that to the same thing in here. And you can see what we're doing is essentially a shortcut to doing this. So I'm going to rewrite that underneath because honestly, that's just kind of a mess. No, I'm going to rewrite that to the side because I'm doing long division and I'm about to give myself 2 inches worth of space to do it. So we have 2.2. I just moved it over. I just moved it over. I went into this whole thing about how I did that. And then I just write it as a 2.2 again. We have 22 going into 160.6. Okay, all right. Not too bad. Now, 22 won't go into 16, so we have to look at the first 3 digits. 22 into 160. Now, I know 2 goes into 16 8 times, but that second digit's going to throw a wrench into things. So maybe 7? Maybe 7? 7 times 22, that would be, well, think about this digit. 7 times 2 would be 14. So I'd have a 4, and 7 times 2, this would be a 14, but I'd be carrying a 1. So it'd be about 154, right? So I think 7's a good number. Let's put a 7 there. And remember, this decimal place goes straight up after we've shifted things around, not before. If we do it before, we're going to break everything and it's going to be off by a power of 10. Or multiple powers of 10, depending on the problem. All right, so we got a 7. We take that 7, we multiply it by 22. We end up with 154. We do our subtraction. And we get a 6. And I bring my next digit down, which is a 6. Oh, well, that's convenient. We can tell that that 22 goes into 66 perfectly, right? 3 times. So I'll put a 3 up here. Take that 3, multiply it by the 22 and put it below the 66. It's 66. Subtract it. We have no remainder. So we are done. 7.3. And if you're ever worried about, if you're ever doing these on paper, if you have to do it on a test or something, and you're like, oh God, I don't know if I did that right. Look at your original problem, kind of round it off and say, is it close to that? This is close to 16, this is close to 2. 16 divided by 2 would be 8. Is our answer kind of close to 8? Yeah. So it's a good way of estimating. Because if I had screwed up and put my decimal place in a different spot, I would have gotten 0.73. 16 divided by 2 is not 3/4. So that would have been an easy way to check. All right, how big is my next one? Do I have, nope, I do not have room on this paper. because I am an idiot and decided to do a large number. I have 413.7375 divided by 4.125. And I wrote this at 11 o'clock last night, which is why we're dividing by a 4-digit number. Because that did not occur to me how ugly this was going to be. So follow along. So we have our 4.125 going into 413.7375. Now we do have to do our shifting thing. I'm not going to bother doing another, like rewriting it afterwards, because all that matters, see, we can see that we want this to be an integer, and we can tell we're going to move it 1, 2, 3 places, right? So that means we have to move this guy 1, 2, 3 places. All that accomplished was that that's where our decimal is, right there. So that means our decimal is going to be right there. That's what that accomplished. So we have our 4 digits here, and we got to figure out where this is going to divide in. So we look at the first 4 digits here and say, hey, that actually does go in. 4125 goes into 4137. All of one time, but it works. I like multiplying by 1. You multiply that 1 onto this thing. We have 4125 right there. I know I got kind of a gap going on here, my bad. Unintentional. If I didn't have awful handwriting, I would, you know, they would line up. So subtract that. And we get what? 12? A grand total of 12 right there. Or my pen is just gonna be awful. Oh, look at the ink dry. It's getting more bold. There we go. All right, so we get a 12. All right. So then you would pull down your next digit and say, how many times does our divisor go into that? Well, it doesn't. This 4-digit number can't go into this 3-digit number, so we'd put a 0 here. Maybe not a 0 that takes up that much room. Put a 0 above that digit and go to the next digit, bring that down. And say, okay, well, how many times would that go in? Again, it doesn't. Right? So we'd put a 0 here again. And then we'd bring down the next digit. You just keep doing this. If it doesn't go in, you bring down the next digit and you put a 0 up here. So you just keep trying. Now we got a 5-digit number. It definitely goes in, right? If you look at it, it goes in 3 times, right? And actually it goes in 3 times perfectly. 3 times 5 would be 15. Carrying a 1, 3 times 2 is 6, plus that 1 would be a 7. 3 times 1 would be 3, and 3 times 4 is 12. Look at that. Past Ben made up a nice problem, even though I thought this was going to be long and horrible. Thanks, Past Ben. You were tired. Not awful, not awful at all. So the main thing to take away from this is what it is you do if it doesn't go in. You put a 0 up here you bring down the next digit. We had to do that 3 times in the same step, quote unquote. And that's fine. It works out that way sometimes. Cool. We feeling good on these? I'm feeling good on these. If we're feeling good on these, that means it's time for the new stuff. I like new stuff. New stuffs are exponents. We haven't played around with exponents yet. Exponents are actually pretty easy. They're not bad. They're weird looking. They're weird looking and they're fancy looking. And if you get the rules down on most of these, you look like a ninja. Luckily, we're not going to go too insane on them. I do have some decent examples in here because we're going to be doing scientific notation in here as well. So it gets a little tricky when we hit that. But exponents are really just shorthands. Like, think about it this way. If I said 2 squared, what does that mean? It means 2 times 2, right? You know that one. 3 squared, 3 times 3. The word squared is saying that it's to the power of 2. Whatever that power is called your exponent. And it's saying that it's actually repeated multiplication. It's saying you have that thing multiplied by itself that many times. So if I have, like on the slide here, 5 times 5 times 5, well, that's the same as 5 to the third, 5 cubed. And that's what 5 to the third means, is you have that thing multiplied by itself that many times. Now, the biggest mistake I see people do on these regularly, all the time. Seen people in calculus do it all the time. Is I see people who aren't paying attention or haven't wrapped their head around it too great, and they multiply it. I see people saying 5 cubed is 15. That will blow up your universe. Don't do that. 5 cubed is actually 125. There's a very big difference. So remember, that 3 means nothing other than how many times you got this guy. So like I just said, there's 2 special named powers. To the second power is generally pronounced squared, and to the third power is cubed. So 5 to the third is pronounced 5 cubed. And sometimes in mathematics, the caret symbol, which is that little arrow pointing up guy, it's used to represent an exponent, such as an exponential power like square or cube. You may see 5 to the third written as 5 caret 3. And in fact, one thing I would like to point out is if you have a fancy calculator, or if you're gonna have a fancy calculator, you might end up with a button that is a caret. And I can use said button to do 5 cubed, trying to get a angle where you can actually read it, because this thing is old before they started putting lights in the screens. 5 cubed is 125, because it's 5 times 5 times 5. So that caret is generally your exponent button. I should actually write that sometimes it's a caret on a calculator, And sometimes it's, I think it's XY or Y, I think it's YX. And that'll be like italic. I've seen that on a lot of calculators. So if you have like a calculator and it has a button like that, a lot of times that's asking for an exponent. I forget if it's XY or YX. I don't have either one, nor have I ever. But it's a possibility. Okay. So we can see that working out exponents can be quite simple, such as 5 cubing 5 times 5 times 5 is 125. But what if we want to go the other way? How can you break 125 into a number with an exponent? Well, that's not bad, because what you end up doing, it goes back to factor trees like we were doing before. You take 125 and you find its prime factorization using one of our many methods. I usually default to factor tree. You end up with a 5 and a 5 and a 5. You take that factor, count how many times you have it, and write that number as an exponent. So you have 3 5s. Congratulations, that's 5 to the third. Nice and simple. And if it's going to be nice and simple, let's do a bunch. Let me write some of these guys down. These go a little bit quicker. I said some of them and I just started writing all of them. I don't regret this. Okay. Exponents. You can tell these aren't bad because I literally wrote them all down on half of the page. So if we are breaking down the first 5, we're breaking down the first 5 into an exponential form. We're breaking it down into something that has an exponent. So you would call it an exponential form. You take whatever number you have, find the prime factorization. So maybe a factor tree. Well, that's 3 times 9, which is 3 times 3. And you say, okay, well, what is the factor I have? 3 of them, right? Or I have 3 right now. But how many do I have? 1, 2, 3. I have 3 of those, right? That is 3 to the third power, or 3 cubed. Same concept, but it works. So 27 is 3 times 3 times 3. Number 2, we have a 4. We know that one, right? That's 2 times 2. Which means I have, my factor is 2. And I have it twice. So we have a 3 cubed and a 2 squared so far. So if you're math dyslexic, both of these problems teach you nothing. 343, little trickier, right? So 343, I don't know what breaks that down into. 343. So I start hitting my calculator on different numbers. 343 divided by 3, that does not go in. All right, no problem. So we try something else, maybe 343 divided by 7. 7 goes in. That's actually 7 times 49. All right. 49 we know. That one is 7 times 7. So this guy, our factor is 7. And we have it 1, 2, 3 times. Okay. Now 72, that one's going to be a little bit more interesting. Because when we factor it, that's 2 times 36, which is 2 times 18, which is 2 times 9, which is 3 times 3. We have 2 different factors here, right? So what you end up doing is you say which factor you have, a 2. Let's start with that one. How many times do I have it? I have 3 of those, right? Okay, so that's 2 to the 3rd. And it ends up actually multiplied. You don't need to put the symbol there because if they're right up next to each other, it implies that they're multiplied. It ends up multiplied by the other pieces. So I have a 3 being squared. So 72 ends up being 2 cubed, 3 squared. Does that make sense? Anybody horrified by that? I'm horrified that I gave myself this much room for 900. Well, let's see if I could squeeze it in there, right? So 900. You know what? Let's call it 9 times 100. I can do that. This 9 is 3 times 3. This 100 is, well, let's just start throwing 2s at this one because I don't want to do 10 and 10 and break them both down. Let's do 2 and 50, 2 and 25, and 25 is 5 times 5. So I have a 3, 3, 2, 2, 5, and 5. I got 2 of everything, right? Now, it doesn't necessarily matter which order I put these in. It's not going to be the end of the world if I do 3, 2, and 5 in this row or in this order. But usually you want them either going up or going down or in some kind of order. If you don't, it's not the end of the world. If you do, cool, that's nice. But I'm going to go ahead and start with the 2 and say I have 2 of those guys. I have a 3. And I have 2 of those guys. And I have a 5. 2 of those guys. That's it. So these really, they aren't too bad, are they? They're really just factor it as far as you go. And then throw them up like that. Now the other ones, the rest of our problems, I'm actually going to move this one down a little bit just to give it some room with that one right above it. But the rest of them, we're going the other way. We have essentially our exponential forms, and we're going to turn those guys back into just standard numbers, into integers. So the 6, on number 6, we have 7 squared. So you should look at that. I'm going to do it just for illustration purposes and say that means that this is 7 times 7 because I have this thing multiplied by itself that many times. So if I see 7 squared, I'm going to think 7 times 7 is 49. Now, granted, it's a little trickier when I go over here to 4 cubed, right? So if you have to, if you don't have a calculator handy, which is fine. I mean, we're kind of doing the classes if we don't. You can look at this as 4 times 4 times 4. And then figure out what a couple of them multiplied together is. 4 times 4 is 16, right? So I could say this is 16 times 4 and figure out what that is. 4 times 6 is 24. 4 times 10 would be 40. 40 and 24 would be 64. So that's what 4 cubed ends up being. 4 to the 3rd power is 4 times 4 times 4. Two to the 4th, or number 8. 2 to the 4th is a little weirder, right? It means you have 2 multiplied onto itself that many times. And if you're like me and you've done a ton of multiplying 2's into powers, if you can already tell what a few of them are, that's fine. If you say, hey, I know that 8, I've factored 8 a lot. And when I factor 8, it's 2 times 2 times 2. If I know that, I can look at this and say, well, that's an 8. So this thing's just 8 times 2, 16. You can do that. You can look at this and say, oh, 2 times 2 is 4. And this 2 times 2 is 4. You can do that. That works. Or you can just punch in a calculator. Hey, whatever. I'm not here to judge you. Now, speaking of calculators, I'm definitely going to use one on this one. Number 9, we have 4 to the 3rd, 2 to the 4th. And remember, if they're right up next to each other like this, it implies that they're multiplied together. So 4 to the 3rd power multiplied by 2 to the 4th power. Well, luckily, those are our last 2 problems. See that? See that? I led us straight into this path. Isn't that beautiful? They just get multiplied. Kind of like up here. If I had 900 right here, this was a 4 and a 9 and a 25. How am I going to put those 3 things together and make a 900? Really, the only way would be multiplication. So these guys right up next to each other implies that they're being multiplied. So 4 to the 3rd, we did that. That was number 7. That's 64. 2 to the 4th, we did that one. That was number 8. That was 16. Actually, I'm wondering. Okay, that's our next setup. Okay. So at this point, you want a calculator. I'm not gonna lie. 64 times 16. Oh yeah, you want a calculator. Now, you could either do that on paper, like we've been doing. You could throw it at a calculator. It does not matter. This ends up being 1,000. Ends up being Ben's horrible handwriting coming back with a vengeance. 1,024. Still a scratchy pen, but it works, okay. So do we have any questions on any of these guys? Nothing worth flailing about? Okay. So let's go back to these. Now we got some more stuff. So when it comes to multiplying exponents, we've already seen what happens if I have two different numbers. I usually call it a base to a power, two different bases to different powers, and you just, break them both down and multiply them together like that last problem, right? But what if our bases are the same? Well, it actually ends up being a lot easier. So a lot of times you'll have to simplify something where it's like 3 to the third times 3 to the fourth, like we have on the slide here. Now, since both of these terms have the same base, which is 3, we can just add the powers together, since there are 3 of them multiplied by 4 of them for a total of 7, right? I mean, 3 cubed times 3 to the fourth. How many 3s do I have all thrown together in a row? I have 7 of them, and they're all multiplying together. I mean, 3 to the third is multiplication, 3 to the fourth is multiplication, so I got 7 of them. So you end up just adding the powers together. 3 to the third times 3 to the fourth is 3 to the seventh. So the base stays the same, the powers add up. So if they didn't have the same base, like we did on the last couple of examples, you would have to work them out separately and then multiply them together. Exactly like that 4 to the third, 2 to the fourth we just did. So that's not too bad. That's not too bad at all. Pausing for dramatic effect. Okay. So, you still writing? Okay, cool. I'm gonna give it a second. The writing is important. If I ever go too fast, let me know. I'll slow down. I'll back up if you need to. So let's do some examples. Let's do some examples. I like examples. You like examples. These examples actually have written a bunch of different ways. Some of them are the same concept, some of them aren't. Okay. So, in these ones, it occurs to me I didn't leave great instructions. These ones, my intention was to leave them in exponential form. I'm actually going to go back into my slideshow real quick and write that out. Yeah. So I meant to say that you want to leave these in exponential form. Sometimes you actually do generally leave it that way, particularly if they're gigantic. Like if I ended up with like 702 to the 51st power, nobody's ever expected to figure that out. There aren't any hard rules about when you leave them in exponential and when you don't. It's usually just a use your best judgment thing. So if you have something that's clearly going to end up being like 50 digits, just leave it alone. If you get something that's going to be 4 or 5, then multiply them together. It's not too bad. Or if you have something, say, like our first one, where I have 2 to the 3rd times 2 to the 6th, and I can say, hey, well, that guy didn't make the ugliest slideshow in the world. So I understand that I'm going to have the same base and I'm going to add the powers together, right? If I have 2 to the 9th, I'm not really expected to multiply 2 out 9 times. A lot of times it's like a rule of thumb, like if I got 5 or 6 things, cool, that's not the end of the world. If I start going higher than that, we're generally just going to leave it as an exponent, unless you're doing like a word problem or something. Now, number 2, we could do this a couple of different ways. I could say, what is 5 squared? 25. And I could say, hey, well, it's outside of this 25, so it's multiplying, and I can multiply 25 by 25. But we're shooting for leaving everything in exponents, which means we want to turn this 25 back. And we know that 5 squared is 25. So this is also a 5 squared. And they're right next to each other, which implies multiplication. You might have the question, should I leave that in parentheses or not? Doesn't matter. It's exactly the same. I could put that in parentheses if I want to. It doesn't matter. It's the same. It's still multiplication. And since it's still multiplication, we do the same thing that we did on the last problem. We got the same base. We can add the powers. And there we go. Now, if I hadn't said leave everything in exponential form, this would be an example of one that you should probably just multiply out, because 25 times 25 is fast to throw in a calculator. 5 times 5 times 5 times 5, fast to throw in a calculator. If it's fast to do, then you generally want to do it. This guy, we have 3 cubed times 2 squared times 3, right? Well, look at that 3. Anytime you have just an integer, think of it as, well, how many of that integer do I have? 1 of them. Think of it like that. And say, if I'm multiplying all these guys together, these guys go together really nicely, right? That 3 cubed and that 3, we could multiply those together and we would have a grand total of 4 of those 3s. As I just completely write it incorrectly, because, you know, I'm here. My sinuses are clogged. I'm thirsty. I'm tired. I got up at 5:30 for work, man, and I'm lazy, so that's saying something. So we got 3 to the 4th. We didn't mess with the 2 at all, right? So that would just be 2 squared. Now, when it comes to leaving things in exponential form, notice that I've kind of interchangeably bounced between having a multiplication symbol in between and not. This would be the preferred way to write it as an answer if you're leaving things as an exponent without a symbol in between, without parentheses like that, because having them next to each other implies that it's being multiplied. So we're already covered by that. And since they're together, it's 1 term instead of 2 terms being multiplied together. So it's kind of a weird hair to split, but that's kind of how it works. Now, again, this would have been one that you would probably throw into a calculator because it ends up being 81 times 4. Really easy to do. What is that? 4 times 8 is 32. So that's what, 324? Yeah. If you can do it in your head at all, you generally just do it. Now, number 4, I wrote this out with the caret because I wanted to show you guys again that this is identical to that. Completely identical, doesn't matter. I can have my parentheses still there. I could not. Mathematically, I could randomly throw a bracket at this if I felt like it. I don't have to. I shouldn't. But I just wanted to show you that like it's just, they're just grouping symbols. They're not too bad. Well, if I got parentheses there already, okay. So just like all the other ones, I have the same base and I can add the powers. 2 and 5, 7. And this is a perfect example of things I would not expect you to work out. 7 to the 7th power, according to my calculator, is 823,543. Yeah, I don't want to do that. So we just leave it like that. So not bad. When you're multiplying exponents with the same base, it's not bad at all. In fact, even when they have different bases, you can clearly see you just work them out separately and multiply them together. Easy, not bad at all, right? We're feeling good. We're excited. We're pumped about math. I love this little meme. The teacher asks if you have any questions, but you sit in silence because you don't even know what you don't even know. I don't sit at home looking at memes all day. I don't know what you're talking about. Okay, so these are a little funkier. I think we're gonna do these ones and then take a break because we're coming to the end of exponents. What all do I have? I keep forgetting I'm gonna go over scientific notation. Yeah, that'll probably be the rest of the class. Whew. So exponents to a power. So what do you do if you have a number with an exponent, or in this case, in my example, I just have x. You have something to an exponent and that thing's to an exponent. So you end up looking at it as it's saying that x squared to the 4th power, just think of that x squared as being a thing. We're saying we have that thing multiplied by itself 4 times. So you kind of look at it as like the outside one first. So you have x squared multiplied onto itself 4 times. Well, because all of these are multiplying together based on what we just learned, you would add all the powers, right? So you'd have 2 plus 2 plus 2 plus 2. You'd have x to the 8th. So because it ends up working out that way, the shorthand way of doing it is you can actually just multiply the exponents. So if you have x squared, oh my God, that freaked me out. It's like, am I tripping? All right. I am in fact not tripping. I am weird enough. I don't do any weird stuff. People have told me they want to see what happens when I am high or drunk, and I'm like, I don't want to see a Ben with lowered inhibitions. That's just a bad idea. So yes, I'm rambling. So we have x squared to the 4th. I'm looking at the bottom row there. That you can just multiply the powers. So you can say it's x to the 2 times 4, which is x to the 8th. So you just multiply the powers. It's great. It's easy. It makes our lives easy. All right, so we got a bunch of examples. I don't know if I regret a few of these or not. There's only one that's kind of like truly tricky. Boils down to sometimes you might just have to do a couple of steps. Yeah. Then we have, I'm writing it out. Sorry if you're impatient and you're like, God, I gotta get to this math now. I'm so excited. I know none of you are like that. I'm just filling the silence with rambling. I am not Depeche Mode. I do not enjoy the silence. That's right. I made a Depeche Mode reference in 2022. Who else has done that this year? I'm probably the only one on the planet. I gotta be unique. I do it that way. It's a terrible way to go. Okay. So we have tons of examples. Some are scarier looking than others. But based on what we just learned, number one, we would literally just multiply these powers together, right? So we would have 2 to the 3 times 2 is what? 6. And so we're just going to use our best judgment on the ones that we can multiply together. So 2 to the 6, I think that's an easy enough one to do, right? Because, I mean, we play around with powers of 2 all the time when it comes to math. It's, first of all, it's very accessible. And second of all, if you ever go into any kind of computer programming, you probably would have recognized 2 to the 7th earlier as being 1024. Right? I didn't just, nope, I screwed that up entirely. 2 to the 7th is 128. Whatever. I haven't done any programming in like 10 years. Whatever. I hated it. It was horrible. Spent 3 hours looking for a problem in a compiler, and it turned out it was a colon instead of a semicolon. Never looked back. All right. So 2 to the 6th power. That we can do, right? 2 times 2 times 2 times 2 times 2 times 2. And if you can, if you recognize that you can see what some of those 2's together are, you can shortcut them, doesn't matter. But we end up with 64. Likewise, same sort of thing happens over here. 3 squared squared. That's 3 to the 4th power. That one's really easy to throw at a calculator. We end up with 81. And I could have told you that because earlier we played around with 3 cubed. That was 27. If I multiplied 27 by another 3, it would have given me an 81. So you can kind of look at them that way. Now this one's kind of trippy, right? So if you run into a problem like this, where you have nested parentheses, where it's just kind of messy. This thing's messy. It's horrible. We don't like it. We don't like looking at it. The easiest thing to do would be to take it as a couple of different steps. Start with your innermost parentheses. Start with the furthest inside and say, okay, this thing, I'm going to kind of ignore the outer stuff and say, oh, well, okay, that's not too much of a nightmare, right? I mean, heck, that's the same as the last problem. That's 3 to the 4th. So you would do that piece And then you'd have something like this. And now you can multiply these powers right here. So that ends up being 3 to the 8th. And this one, I think we will throw it at a calculator, not because I think it'd be fun to multiply this thing out 8 times, but because on our previous step, you could see it's 3 to the 4th squared. Well, we just found that. That was 81. So this thing is actually, if we have 3 to the 4th twice, that gives us 3 to the 8th. So this is 81 times 81. I'm going to kind of write that down here. So that's 81 times 81. And according to Mr. Calculator here, that's 6,561. I would never look at that number and say, I bet that's a bunch of 3s. All right. Hey, look, we have light algebra. It's algebra light. We like algebra. We haven't done any of it. It's algebra light. Actually, we have done a little bit of it. Whatever. What do we do when we have these particular things? There is literally no difference. My A is still a base. I still have a power of 2. That power of 2 is happening 10 times, which means I have 2 times 10. I get a 20 right here. That B, right next to it, has a 5 already, 10 times. So that's a 50. What else can I do with this? Literally nothing, because I have absolutely no idea what A and B are. You take it one more step into an algebra class, you'll see a little line that says let A equals 2 and B equals 3, and then I just swap them out and call it good. Because there's no way in hell I would say punch 2 to the 20th into my calculator. Well, not on paper. I could punch it in my calculator all day. That's 1,048,576. Which is a megabyte, because I'm a freaking nerd. Okay. So let's look at this guy. This guy's kind of funky. He's exactly what we had earlier, but he's squared now. We already played around with this. What did we do before? Let's ignore that set of parentheses. Let's just look at the inside. This 5 squared is multiplied by 25. What's 25? 5 squared. Okay. Well, let's put those together. 5 squared times 5 squared. I would add the powers. So I would end up with 5 to the 4th. Okay. Well, now I have 5 to the 4th squared. I have this thing twice. So if I have 4 of them twice, I have 8 of them. What is 5 to the 8th? Whew, 390,625. Yeah, you wouldn't be expected to find. So you call it good. How do we feel about these? They okay? They're horrifying? They're weird? Any questions? And it's literally just being more about manipulating them right now than it is, here's your goal, find your answer, blah, blah, blah. Sometimes we can get a nice, neat number. Sometimes we can't. Sometimes if we had numbers, we wouldn't want to anyway. It happens. We get nice little numbers, we can do those. Is there a rhyme or reason? If it's horrible. If it's horrible, you don't. If it's not horrible, you do. How do I know if it's horrible? You do 100 of these, and then you got the idea. All right. So before we move on, I have been talking for an hour and a half straight. It is break time. I want a break. You want a break. Let's take a break until 7:45. I'm gonna make a random slide, 7:45, back from break. And for the time being, I am going to shut up. Do what you gotta do. All right, everybody ready for more math? Yeah, you're all excited. Hit the slideshow button. How much can I see here? Okay. So, radicals and roots. Roots or radicals, I guess I should actually edit this a little bit. It's not quite the same thing. The symbol is called a radical. They are the opposite operation of applying exponents. That's the reason we're learning them at the same time. So we can undo a power with a radical, and we can undo a radical with a power. Square root is the opposite of squares. Cube roots are the opposite of perfect cubes. This scales up to any power necessary. Now, that doesn't really tell you a whole lot. So this is a little bit more of an example. So we've already been working with exponents, so you can recognize some squares and cubes a little bit easier. So that actually translates really well to the concept of square roots and cube roots. Usually in normal math classes, you'll be taught square roots for a little while, and then they'll teach you cube roots for a little while. But I honestly just think it's easier to teach them at the same time. It's the same rough concept. I mean, squares means you have 2 of everything. Cubes means you have 3 of everything. So what ends up happening is these are kind of the opposite way around. If I have the square root of 4, that's a 2, because it's saying, hey, what squared is 4? 2. So the square root of 9 is asking you, what squared is 9? Well, 3. And it's a little trickier when you get to cube roots. So if you know cubes a little bit easier, like 2 to the 3rd is 8, you might be able to look at the cube root of 8 and say, oh, okay, well, I know 2 cubed is 8. So that means that the cube root of 8 has to be a 2. So it's the other way around. And you might look at this and be like, oh God, I'm not going to get this. This is weird. And actually, I have a nice way of teaching it. And I was actually very happy because I believe I was looking at the essential ed stuff, and I think it actually went with the same way I like to teach it. So I thought that was kind of cool. Doesn't happen very often. So this is a basic look at simplifying a square root. It's a couple of different ways you can look at it. So if you're simplifying a term that contains a square root, what you do is you take out anything that's a perfect square. So what you're actually doing, you factor the inside of the radical. So you look at that 4 and you say, oh, well, 4, that one, its prime factorization as an exponent would be 2 squared, right? Because it's 2 times 2. And anytime you have a perfect square, it comes out. It essentially breaks down because the square root of a perfect square kind of cancels. That concept cancels out. So you look at this and say, oh, well, I have the square root of 2 squared. The square root and a square cancel. So it's just a 2. So the exact same concept works with cube roots. And the way I like to do all these when I'm factoring them is factor trees, but I really didn't want to try to figure out a nice way of putting that on a slideshow. So you guys see most of that on the examples that we do. So cube roots work. It says similarly, exactly the same concept as a square root. You can see that any perfect square comes out of a square root. The concept works exactly the same with larger roots, such as cube roots. So same thing I'm retreading here. The cube root of 8 is 2. We already covered that one. That's because 8 is 2 cubed. You're taking the cube root of a perfect cube. So since you have 3 of that factor, it comes out similar to with a square root. If you have 2 of that factor, it comes out. That's a better way of explaining it, and I probably should write that down. So larger roots than square or cube. So what happens when we have anything larger than a square? So a cube root, or after that, it doesn't have a fancy name for it. So a 4th root or a 5th root or a 100th root. The same thing happens, exactly the same. It's the same concept. If I have a square root, I need to pull out 2 of the factor. If I have a cube root, I'm pulling out 3 of the factor. 4th root, you have to have 4 of the factor to pull back. 5th, you need 5. 6th, you need 6. 100th root, you need 100 of a power. If I have the 100th root of 5 to the 100th power, it's a 5. Like it just works. So I got a bunch of examples. I like these examples. These are nice examples. I like them. You're going to like them. We're definitely not going to finish even scientific notation tonight, now that I'm looking at the clock. I thought we'd be a little bit further now. So let's just worry about number 1 at first. So the idea here is that we're going to simplify. You're going to see the word simplify in math problems a lot. It basically just means break it down until you can't break it down anymore. Make it not ugly. Square root of 144. That's kind of ugly. We don't like it. Now, if you know all your perfect squares, if you've done this a lot and you're like, oh, I recognize that 144. I recognize it. That's the perfect square of 12. You could very well say, oh, hey, I know that's the perfect square of 12. I know it's the perfect square of 12, so the answer is just going to be 12, because the square root of a perfect square kind of cancels out. But let's say you don't know that. Let's say you have no idea. That confuses you horribly. You're like, Ben, what the hell did you just do? I don't understand at all. What do you do if you're lost, if you're stuck, if you're confused by this entire concept? So essentially, roots are exponents backwards. Instead of scaling up, you're now scaling down. So what you want to do is the easiest way to do these, even if you have like a 10-digit number and you have no idea how to start, just do a factor tree. Break these guys down. And you can do it simple. I could look at this and say, I don't know what goes in there, but it's even. So I could put in a 2. That's a 72. Well, it's even. I could pull in a 2. All right, that's a 36. That's even. Another 2. 18. Still even, still 2. 9. Oh, and then I got 9 is 3 times 3. Now this is the way I do these. And you'll want to watch for a second here. The way I do them personally is a little bit off it still tracks great with all the books and everything. Don't get me wrong, but it's a little bit different. Because what I like to do is I like to look at it, and anytime I have 2 of a factor, I circle. Because that's a perfect square, right? 2 times 2, that's a perfect square. Well, I'm square rooting it, right? So what's the square root of a perfect square? Just a 2. Every time I circle something, it's going to come out of the radical. It's going to come out. Actually, that makes me think of something. Let me look. Okay. I am going to have an example of what I just thought of. Okay. So again, I have another one. So another 2 comes out. I have another, those 3s. That's a perfect square. That's 3 squared. That 3 comes out. Now I get a lot of people who are confused as to why anytime I pull something out, these are all multiplied. I always get asked this every semester, everybody I've tutored, everybody's a little confused. Why do these all multiply together? Because these all multiply together. This is 2 times 2 times 2 times 2 times 3 times 3. So if I'm square rooting them, it's still multiplication. You just have less of it. So everything that's a perfect square can come out of the square root, and we managed to pull off everything, right? We pulled out a 2, we pulled out a 2, we pulled out a 3. You multiply them all together, you get that same 12. Was that more work than recognizing it's a perfect square already? Yes. Does it get to our answer? Also yes. That's really what matters. Can we figure out a way of doing these when we have no idea what we're doing? Yeah, absolutely. Let's look at another. This one is a little bit different. We have the square root of 75. Now this one is not a perfect square, right? But we recognize 75, that's 3/4, right? And a quarter is a perfect square, 25. So if I broke this guy down, that's 3 times 25, and 25 is 5 times 5. Okay, all right. Not too bad. So the same thing happens. I have 2 of those 5s, so I'm going to circle them, which means I'm square rooting a 5 times 5. The square root of a 25 gives us a 5. Now, in this particular example, it's a little bit different because this 3 didn't come out. It doesn't have a pair. So what happens when that happens? Nothing. It's still in there. It's still hanging out under that square root. It sucks to be that 3, but it actually ends up still being there. You just draw the square root again and write out what you got. And for that matter, I'm not 100% if I have a good example for what I want this to lead into, so I'm going to do another random example. Let's say we had, it's just a random example, it's not on the slideshow. Let's say we had the square root of 375. Now, if I factor this one, I mean, the first thing that comes to mind is that it's 5 times something, ends up being 5 times 75, which we just did. So that one is 3 times 25, which is 5 times 5. So the same thing as the last problem, just with an extra 5, right? What I wanted to show you guys is the 5 still comes out, but what happens if I have multiple items on the inside? And it's similar to the question I get posed right here. Why do they get multiplied together? Because they're already multiplied together. Inside, I have this times this times this times this. I just pulled these out. These are still multiplied together. They are still multiplied together. So you multiply them and you call it good. Feel like maybe I should switch to boxing answers instead of circling because I'm circling so much on these pages. Okay. Let's see. What's my number 3 is 4,500. The square root of 4,500. Oh God, oh geez, what do I do? It's a 4-digit number, oh God. But the last 2 digits are zeros. And if the last 2 digits are zeros, this is 45 times 100. Now, one thing that's nice about the tree diagram method is sometimes you'll look at this and say, oh, 100, I mean, I could break that down by 2s and 5s and everything, but I could also just call it 10 times 10, and a 10 would come out. Because I recognize that perfect square. If you don't, that's fine. It's not a problem. But that's something you can do. And then you just have to break down a 45. That's 5 times 9, which is 3 times 3. Hey, look, a 3 comes out. So the way my structure of doing these always ends up being going, I make a tree diagram. Anything I have 2 of, I circle. Everything I just circled comes out as 1 of that. And they all get multiplied together. And then I start a square root, and anything that's left inside gets multiplied together as well. In this case, I just have a 5. And if I just have a 5 there, that's the only multiplication I have to do is the 10 times 3. Not too horrible. Any questions on these so far? Flailing, confusion? Nobody freaking out? We've played around with tree diagrams a lot so far. It's not too bad. Let's keep going. What's my next one? I have the square root of 24 times the square root of 6. Is this 4? Yeah. Remember, anytime you have 2 things right next to each other and they don't have a symbol between them, it's multiplied. So these 2 guys are multiplied. Now, this is actually a really good example. Do I have another example of what I wanted to cover here? Not at all? Okay. This is another one I'm going to have a random example afterwards. But what ends up happening with this guy, because the square root of 24 breaks down a bit. It breaks down a bit. And the square root of 6 doesn't at all, right? I'm going to do this one twice because there's 2 different ways I can see how to do it. And because of that, I want to show you both ways so that whatever impulse you have when you see a paper problem like this that you have to do, and you're like, oh God, which way do I go? I don't know, it doesn't matter. First impulse. My first impulse when I look at this is that a fun, funky rule that you can run into is that if I have a square root times a square root, you can actually multiply the stuff together inside. You can actually multiply it together inside. Now you have a choice. Because normally you would multiply these two numbers together, right? But let's say I don't. Let's say I don't. Because what's a factor tree going to do? It's going to break things down into the prime factorization, right? Well, if it breaks things down into the prime factorization, it's going to be the same numbers anyway. So everything here is going to multiply together one way or the other. So I can just factor them both separately because they're already being multiplied. And you'll see in a second that this is a terrible example. And I need to change this one next class, next time I have a class. Because I figured this out last class I taught over the summer or fall. And I was like, I need to change this. And I didn't. I'm gonna forget this time too. I'm gonna say this again in a few months. Exact same thing. So I have it fully factored. I don't really have a nice way of circling things, right? Like I'm looking at this and I'm like, I could circle these two and this, I'm gonna do that. And I'm gonna do that. They don't line up too nicely, but as long as I can see what I'm doing, I'm good. And I can see that this is going to be a 2 and a 2 and a 3. Yes, that's an ugly 3. I'm sorry. Okay, so what is that? Hey, it's a 12. Because 24 times 6 is 144, and we already did that problem. That's why I said it was a stupid problem. And I should have fixed it. But I didn't. Now, this was one way of doing it. Remember, we're not worried about the numbers, we're worried about the method. If you can see that you have something like this, and you're going to end up multiplying the stuff on the inside of the radical together and then breaking it down, cool. That's a great way to do it. That's exactly what you want to have in your head. The numbers themselves on this problem, I don't care. I don't care, you don't care. It's all about the method. Speaking of methods, this is a little funkier. This is a little funkier, but another way to do this problem is ignoring the fact that this square root of 6 doesn't do anything. So we just say that's just going to stay there. And you can break down the 24. 2 and 12, 2 and 6, 2 and 3. All right. Yeah, we saw the fact that this wasn't going to go together perfectly coming because the square root of 6 is still here. So this 2 would come out. But what do I have left? The square root of a 2 and a 3. And that root 6 is still there. Well, what's this 2 times 3? It's root 6. Oh my God. I have a root 6 and a root 6. I have 2 of something. We just learned what happens when we have 2 of something multiplied together. We can have an exponent. If I have an exponent, what happens if I'm squaring a square root? That's a 6. The square root of 6 squared is a 6. Multiply them together, we got a 12. Again, it's another way to do it. Obviously, the other way was a little quicker. But I wanted to go over it this way so you could see, one, if you went this way, you could salvage it. I've seen a lot of people do math and just go a completely off the wall direction and say, oh, you know what, I'm gonna erase it all and start over. Sometimes you just fix it. It's fine. You end up here and they're like, oh God, 2 root 6. Yeah, just multiply those guys together. You're good. You're fine. One thing I did want to cover, this is a really quick little example here. One thing I did want to cover, I don't really know what numbers to do. Really basic, because I showed you that if you multiply stuff together, if you have 2 radicals side by side and they're multiplied, you can multiply the stuff inside together. What happens if I have something like this? Exactly what you might expect. The stuff outside multiplies together. The stuff inside multiplies together. That's it. That is the concept I wanted to throw at you. I don't think I have any of these problems like that. So that's a good one. It makes sense, right? Because all of these are multiplied together. 2 times root 3 times 4 times square root of 2. And you can multiply them together in whatever direction you want. I always say you can regroup these. It's the, it's the commutative property of multiplication. Okay. Back to our normal type of problem. Except now we got the cube roots instead of square roots. I set us up for the most basic of cube roots. Cube root of 27. Cube root of 27 ain't bad. All of these, just factor tree first. All of them. And then, well, with the square root, anytime I had 2 of something, it had to come out, right? But now we have a cube root. Anytime I have a cube root, I need that many. I need that 3. Well, how many 3s do I have? 3. I'm going to circle groups of 3 when I have a cube root. Square root, power of 2. I'm going to pull out 2. Cube root, power of 3. I'm going to pull out 3. If I had a 4th root, I would need 4 in a group. 5th root, 5 in a group. That's what that one slide was saying. This concept of breaking these down, the reason I do them this way with the tree diagrams and circling them is because this will apply to every single power of a root. Every single one. 5th root, 100th root, doesn't matter. If you have that many of a factor, it comes out. And that's why I don't understand why these things are taught in at separate times, because it makes perfect sense to teach them at the same time. Number 6, cube root 108. Cool. Break down 108. 2 and 54. 2 and 27. Well, 27 I know, right? 3, 9. 3 and 3. Okay. All right. So it's cube root, which means I need 3 of something to come out. We already know that this 3 is coming out because we had that 27 there. The main reason we have this problem is because we have 2s here. It's kind of a trick because up here, if you had 2 of something, it would come out. Here, it's cube root. I only have 2 of those 2s. So they're stuck. That 3 comes out. But inside the cube root, I still have those 2's multiplied together. So I end up with 3 cube root of 4. Or another random vocab lesson. The number right here is called the index. It's the index of the radical. That's one of the few I've actually used in the past, because I have done higher problems of these, like 5th power or 5th root, 6th root, etc. Sometimes it's useful to tell somebody, hey, the index is supposed to be a 5. And there you go. All right. Got 2 more of these. Oh, God. And then we're probably going to end up breaking up early, because there's no way I'm going to be like, okay, scientific notation exists. We've hit that awkward point where I'm about to introduce a large thing that has a lot to do with exponents. But it really should just be like, scientific notation is something that's usually taught as its own class, and I don't argue that. So in this case, I mean, you might see something coming, because earlier I had what, 4,500, I pulled out 100. Hey, look, I got 125,000. Guess what Ben's gonna do? There's 125. There's 1,000. Easiest first step you'll ever do. I'm gonna be cheap about that 1,000. 1,000 is 10 times 100. 100 is 10 times 10. 125. That's 5 times 25. 25. That's 5 times 5. Right? Beautiful. Look at that. It's a cube root. I got a bunch of cubes. I got a perfect cube of a 5. I got a perfect cube of a 10. What do I got? 5 times 10, 50. Nice. Now, if I hadn't taken that little shortcut with the 1,000, I would have ended up with 3 2s and 3 5s. I mean, look at 10. I could have split each of these as 2 and a 5, 2 and a 5, 2 and a 5. Would have worked out the exact same. I would have pulled out a 2 and I would have pulled out a 5 instead of a 10. Would have worked out exactly the same. And number 8. We have a cube root of 2 and a cube root of 4 multiplied together. Oh man, when I review this next class, I'm going to make some really off the wall problems. I got some ideas. Well, notice that the square root and the cube root rules were very close together. Same idea happens here. What happens when I have 2 cube roots multiplied together? I can have the cube root of those guys multiplied together, which I can already tell that 4 is going to break down into a 2 times a 2. So cube root of a bunch of 2s. Just 2. Cube root of 8 is 2. It's the same problem as on our first example. We've come full circle. Woo! All right. So, like I said, I really don't like the idea. I mean, look at that number. I really don't like the idea of starting to explain this. And then, yeah, because before we even get to the first example, there are 5 slides. So we're gonna do that next class. We are done for the night. You guys are free. I am gonna round it to 8:30 because they're gonna pay me for that, that 1/6 of an hour. I want my $3, $4, I don't know. So yeah, you guys are free. Have a good night. We're done. I don't know how to end the class. I don't know how to end the class. I'm awkward. I'm done. Go home. Good night.